one additional energetic property of aqueous solutions that we need to consider, in addition to all these weak interactions that we've been talking about. This energetic property of aqueous solutions is central to the conformational properties of most biological molecules, biochemically relevant molecules. And it's essential for understanding their stabilities. And this is, of course, known as the hydrophobic effect. Now, consider the following example. If I took a container and to this container, I introduce some water, and then I also introduce into this container an immiscible solvent of some kind that's not miscible with water. It's less dense, and so it's going to float up here on the top of my water in this container. All right. So down here we've got water, and up here we have an organic solvent. Okay, so of course we know if the solvent's immiscible with water, we're going to get this nice phase separation. Now, what happens if I introduce into this tank through, say, maybe a pipe of some kind? Let's say I take some methane and bubble some methane through this pipe into this solution. Here's my question. Where does the methane go? Where does it mostly want to be? Where do you find it if you were to go looking? Is methane soluble in water? No, right? The methane is going to end up concentrating in a big way into the organic solvent because it's not soluble in water. Okay, well, why? Why does it end up in the solvent? Right? We know it's going to happen because we kind of have been playing around with oil and water probably since we were kids. So we have an intuitive understanding that that's what's going to happen. But the question is then why? Okay, well, consider this. We can think about that process as an equilibrium. So we can write that down. We know how to write that down, right? So we could say, well, let's think about this as a methane in water that's in equilibrium, say, with methane in the organic, right? And we know from everything we've been talking about up to this point that we can write down for that equilibrium, we can write down an equilibrium constant. And we know how to define that equilibrium constant based upon our discussion last time. And that's simply that the equilibrium constant for this process is going to be equal to the concentration of the methane in the organic solvent divided by the concentration of the methane in the water, right? So that's pretty cool. That's in principle something we could measure. There are all kinds of tools we could use to make that measurement and do it actually pretty precisely. And it would basically tell us what we already know, that the methane is going to want to be up here in the organic solvent. But again, we want to know why. Why does it want to be up there? Well, if we know the equilibrium constant, based upon the discussion we've had over the last couple of lectures, we can specify the energy distribution in the system. Remember, there's this incredibly useful relationship between the equilibrium constant and the free energy. And remember, assuming we've let the system come to equilibrium, which is what the EQ means, we know what has to be true is that the standard state free energy for this system has to simply be equal to minus RT natural log of that equilibrium constant. That's kind of cool, right? And it turns out that you go do this kind of experiment, and people have done it with great precision in lots of different ways. And you think about this system, I'm going to write it slightly differently as sort of methane in water versus methane in an organic solvent. And sometimes this will be referred to as a partitioning equilibrium. Turns out that if you go and take the experimental measurement of a system set up this way, what you find it depends on the solvent, but I'm just going to give you a number for, I don't remember exactly what solvent was used in this case, but this is an actual experimental number. What you find is that the delta G naught at 25 degrees Celsius for that equilibrium is going to be equal to minus 11 kilojoules per mole. Okay, that's great. As written, that would make some sense. That means the equilibrium constant is consistent with the methane being in the organic. The free energy balance as written is negative. So the transfer of water molecules, transfer of the methane molecules out of water over into the organic solvent makes all the sense in the world based upon that free energy difference. Okay, good. Why? We still don't know why, right? It's just sort of we've quantitatively confirmed our intuition, but why does that happen? Well, this is the beauty of the kinds of things that thermodynamics allows you to do. You can break this down because you guys hopefully all remember, of course, that we can take that free energy, that delta G naught, right? And through the Gibbs equation, we can break it down in the constituent enthalpy and entropy terms, right? Through the Gibbs equation. And it turns out there are ways you can do this, right? We're going to see an example of this soon, or you guys are. Turns out when you do this, that for this process, the standard state enthalpy change for that transfer of methane from water into an organic solvent is plus 11.7 kilojoules per mole. Now look at that number and think about the Gibbs equation for a second. That should make you sit up and go, wait, what? Wait a minute. Remember, we just established that this transfer of a methane molecule out of water into an organic solvent is spontaneous. It's energetically favorable by minus 11 kilojoules per mole. Remember, a spontaneous process has to have a free energy change that's less than 0, and it does. But the enthalpy change for this process is not only large, it's large and positive. And if the enthalpy change is positive, what does that mean for its impact on the free energy? It's going the wrong way. The enthalpy change for that transfer actually opposes the transfer of the methane molecule from the water into the solvent. Now, what that has to mean is that there are a set of favorable interactions of some kind in that system that enthalpically oppose the transfer. Yeah, that bend your noodle a little bit. We'll come back to that. Okay, but this still happens, and because we only have one other component to the Gibbs free energy, we know what the answer must be that's coming up, which is that if we look at the entropy term, and I'm just going to write this as minus T delta S, because that's a little bit easier, that is minus 22.6, in this case, kilojoules per mole. And this is really like, okay, I understand it again. You add those two numbers up, you get the nice close to a minus 11 kilojoules per mole. And in this case, the entropy change of taking that methane molecule out of the water and sticking it over in the solvent, the entropy change completely dominates the free energy and drives this reaction as a spontaneous transfer of water, of methane out of water where it doesn't seem to want to be and over into the organic solvent. So that all makes sense. Whew. Now I got it again. Okay. Now this is an example of the kind of energetic trade-off between the components that go into a process, the free energy components that go into a process, that you're going to see over and over again. We're going to come back to this when we talk about protein folding in particular. The fact that the enthalpy and entropy of a process are both important, and they can reinforce each other or they can oppose each other. And this is an example in this transfer where they oppose each other and the entropy change wins, right? But that doesn't always happen. All right, so that's cool, and that's really kind of interesting. Now the next question is, where does that big entropy change come from? Why is this such a entropy-dominated process, this transfer of water disliking, which of course we would call hydrophobic substance, out of water and into a solvent? Well, one of the things that you may remember is that water is really unusual. It's a very, very special molecule in terms of its physical properties. And in both its liquid state and its solid state, it does some really amazing things. And this phenomenon is based in some of those properties. So what's something that you know, hopefully, or you remember, that water really loves to do? It loves to hydrogen bond, right? We just talked about hydrogen bonds. We talked about the fact that it has a permanent molecular dipole, right? And those are going to interact. But one of the things that water molecules, especially in liquid, or also in solid, in an ice crystal, but in liquid, even though these water molecules are flitting about and doing all their rotational and translational things, right, in liquid water, they're not, in any sort of like regular order. They're still hydrogen bonding with each other. There are these flittering networks of hydrogen bonds, making and breaking on sort of, nanosecond or sub-nanosecond time scale constantly in liquid water. And that's one of the things that makes water really unusual as a solvent, gives it some of these surface tension properties and some of these other properties that make water very, very unusual, very special. And it really, really wants to do that. Now, that property, the fact that it's got great hydrogen bond donors and acceptor, the oxygen molecule is a great acceptor. The hydrogens are great as donating hydrogens from the oxygen to the oxygen of another water molecule in hydrogen bonds. This makes the molecule really polar, on top of the fact that it's got that permanent molecular dipole. So water interacts with polar substances like, for example, salt crystals or other polar objects, right? It's extremely good at solubilizing them. It can orient those dipoles around charged groups. It can hydrogen bond with stuff. The hydrogen bonds, even if it's not a hydrogen bond donor, those polarized bonds are going to interact along with the molecular dipole to just beautifully solvates charged and polar solutes. But if you think about methane, it doesn't have any groups like that. It's not charged. It's not particularly polarizable from the point of view of creating dipoles like we talked about before, certainly not by water. Electronegativity between carbon and hydrogen is not so great that you're going to get a really nice molecular dipole out of it. In addition, it isn't, going to interact effectively with water through a hydrogen bonding interaction. Carbon's not a decent hydrogen bond is not a hydrogen bond donor or acceptor. So the methane molecule can't interact with water in all of these ways that polarized charged solvents or polar solvents can. But I didn't give the water a choice. I set up my little pipe and I turned on and I pressurized it up and I rammed the methane up in there. It had to go in there. So the water didn't have any choice but to make a cavity, right? I shoved these atoms of molecules of methane into the water. it's going to go somewhere. The water has to rearrange its bulk structure to do something. You know, if the mass is coming in, it's got to go somewhere, and it has to make a cavity. But the cavities that water forms, since it can't solubilize this stuff, are very unusual. Water molecules will sort of have to get out of the way, right? But because they can't solubilize this hydrophobic molecule that's being shoved in there, they do a couple of really interesting things when they form these cavities. One of the first things the water molecules appear to do is they orient themselves to try and sort of, as any molecular interaction like this, as we talked about a little while ago, to maximize the van der Waals interactions. But the other thing that they do is they form these networks of hydrogen bonds around the surface, right, of the cavity where they interact, where this hydrophobic stuff, the cavity gets formed. And these hydrogen bonds that get formed around the periphery of these cavities are not like the hydrogen bonds formed in bulk water. They have the same basic properties in terms of how the molecules are oriented, but they're much longer residence time, and they're more consistent, people think, with something like ice. So it's almost like the water molecules form these little monolayers, or maybe slightly thicker layers, of high residence time water molecules around these cavities that are sometimes described as ice-like. Some people also refer to these as clathrates because of what they look like, right? So these water clathrates around these hydrophobic molecules have a couple of interesting implications for the overall energy distribution of this nonpolar stuff stuck in water. The first is, imagine, you think about the formation of these hydrogen bonds, right? They get formed. Is that, from a enthalpic point of view, you're forming a nice stable bond. That's an enthalpically favorable thing to do. That's going to release some heat, right? So the formation of these hydrogen bonds is super enthalpically favorable, and that's going to contribute a negative enthalpy to the presence of this hydrophobic stuff in the solvent. In other words, the hydrogen bonding itself, this high residence time hydrogen bonding, clathrates of water, is enthalpically favorable because of the strength of those hydrogen bonds, right? However, there's a price, and the price is that you're putting making this cavity for this hydrophobic stuff, and the formation of these clathrates is essentially forcing the water to form an ice-like structure at, say, room temperature 25 degrees, where ice is not stable, and there is a gigantic enthalpic penalty. Making the structure like this may have a favorable delta H, but it also has a very unfavorable, it has an unfavorable entropy term, right? So tying those water molecules down in these high residence time clathrates or cages has an entropic penalty for the water molecules compared to their state in bulk water, right? And the issue that arises is that even though these hydrogen bonds are enthalpically favorable, they're so entropically expensive that if you give the water an option, it's going to minimize the energetic penalty. It's just a sort of a general property of thermodynamic systems like this, that they will tend to seek out the minimal energetic penalty. And that minimization results in a couple of things. One thing it's going to try and do is minimize the number of water molecules that are tied down, that are contributing to this unfavorable change in entropy. All right. The other thing that it's going to do is look for, or the system is going to seek out other sources of energy optimization. And the hydrophobic the van der Waals interactions between these nonpolar solutes with themselves compared to the water molecules is a whole lot better right. They interact with themselves much better than they're going to interact with water. So that is going to provide, when these guys interact with themselves, a quite favorable enthalpy term, right? So the system, in an attempt to minimize the overall energetic penalty, right? It would be better if the hydrophobic stuff wasn't there, but since it's there, we got to make a cavity and we got to minimize the penalty. And that minimization is minimized by, number one, gaining as much enthalpy as you can from the high residence time hydrogen bonds of these clathrate structures, clustering the hydrophobic stuff up together, and minimizing the number of water molecules that contribute to this entropic penalty. All of those things together result in the tendency of hydrophobic stuff in aqueous solvents to clump together, right? That clumping together, that clustering of nonpolar solutes in aqueous solution is the definition of the hydrophobic effect. And it's coming about as a result of an attempt to minimize the energy penalty. And you do that by, or the system does it by minimizing the number of water molecules that participate in these clathrate structures and maximizing the enthalpic gain of the nonpolar van der Waals interactions between the solute molecules. That means they're going to tend to stick to each other and they're going to tend to form spherical type structures because the entropic penalty of the water molecules is going to scale essentially with the surface area. The gain in enthalpy of these hydrophobic molecules is going to scale with the volume. So by clumping the hydrophobic stuff together, you minimize the number of water molecules that have to interact because you minimize the surface area, and you maximize the interaction between these hydrophobic molecules within this large hydrophobic volume in which they interact with each other. And that tendency to cluster stuff up is the definition of the hydrophobic effect. And we're going to come back to that as a really important property of polypeptide structure in water when we talk about protein folding.